hopefully we will be able to answer your questions. You're writing that how can you put the CO2 down? Where we can put it down? And what are the parameters over there? Can I put it here or not? So what do we do? So what steps we need to take? So I'll not make talk and presentation. I think it's a discussion. Try to make it short. If you have questions, definitely we can continue during lunch. Typically, we try to put a figure which depicts everything. If you see, whenever we put it on the sea, we call it basically offshore, and whatever on the ground, we term this onshore. And if you see, few of the things are there, like when basic strata of the earth, when you go down, there are different types of rocks are there, which is a porous rock, which is a non-porous rock. We have some water level, we have some water, liquid and solid mixed level of this. So the first thing to test is what is the strata of the which is liquid. We talk about another thing, absolutely on the other side of this, wherever we can capture the CO2. If you see that one thing is clear, if we are putting it in the sea, and if it is below 3 kilometers of level, if we can theoretically we can put a pipeline 3 kilometers down the sea and release the CO2 would never see the surface again. Because it will sink, if you see from the 3 kilometers down, the pressure already will be having the water color pressure of this, it will force CO2 to go down. So if you see on this side, here it's sinking CO2 over there, and it comes down and it forms a CO2 lake down, which is around 4 to 5 kilometers or below. So if we can, theoretically, if we can put it down below any time over here, and it will automatically reach the bottom of the earth. So it might be the easiest way, because once it is going to the bottom of the earth, and it will have automatic mineralization, so it will conform to the liquid and ultimately form to the hydrocarbon. So that's one of the things we can do. And process of basically petroleum development has happened. It's a natural process which Earth invented for millions of years. Now, if we can come out with this storing CO2 on the underground, we see few of the things we can do it in the coal seams. We try to put few dimensions on this slide. The capacity typically should be 40 gigaton, or less than 2% of the emissions of 2020 we can put under the coal seams, which has been identified. CO2 EOR, so enhanced oil recovery. So we can find out the existing oil reservoirs which are depleted heavy, which is having a capacity of 920 gigatons, theoretical capacity that we can put it. We'll come back what are the selection criteria for this reservoir, we will come back. But 45% of the emissions, and finally deep sea aquifers, which is, you see the value, which is 400 to 10,000 megatons, which is going to 500% of the emissions by 2020. So ideally, if we can develop a technology where we can put the CO2 below 3 kilometers of the emission level, ideally we will be set. Because it will never come up, it will go down and down and down, and ultimately it will form a liquid, and from liquid it will convert to the hydrocarbon. So that's the basic three type of storage can be. Now, We come up with the absolute, come straight to the point that can any place, what qualifies for a storage space? Now, let us take two things straight up. CO2 enhanced soil recovery, so CCS, when we are talking it and putting it back to the ground, the purpose of enhanced soil recovery and purpose of storage purely has two different things. Absolutely two different things, and we have to make it very clear. We don't have much choice while we are talking about the CCS enhanced soil recovery. Because anyhow we have to take the oil out. So we have options like we can, once the pressure of the reservoir comes down, we have option one is that pump water down. Option two, pump steam down. So Oman is one of the countries where actually generating steam. So burning fuel gas, generating steam, pumping the steam down. Third is we use the fuel gas or associated gas, whatever is coming out. And some of the fields, like one of the Abu field, ADCO, they are getting almost 10% CO2 coming up with the associated gas. They are separating and putting it back. So it's already there. And wherever you get CO2 available, like Northern Sea, we are trying to do that here. So we don't have a much choice of what geological strata over there. We want to do it absolutely for a different business purpose. Whatever the strata we don't mind, we need to put up the oil coming out. And by this process, there is called breakthrough. Breakthrough means the amount of CO2 I am pumping in. When the CO2 is coming out from the oil, that ratio is more or less there. So that's a breakthrough period. Till that, whatever the CO2 has gone underground and is getting stored, fine. After that, there will be no further theoretically, no further CO2 storage. Whatever goes in comes out.
Shall we so directly see what it is saying?
Yes, you can.
There is no possibility.
No, there are few of the issues coming out. Number one, which is called acidification. The moment you put CO2 in the water, the acid will fall. Now, we really do not know if we can talk about the previous one. Sea is having acidic. However, sea is a host of different flora and fauna and resident habitats. This is not very clear with the environmentalists. Whether do we have a right to kill others or not, which is still not being answered. So we'll pull the sea, and typically the sea is the good thing is once you put it down, I'm sorry to repeat this, you put below 350 kilometers, it will never come up, it will go down and down and down till it reaches the bottom. And when it reaches the bottom, there will be acidification of the surrounding area. So obviously there will be some species who will be affected badly. And if some species are affected badly, the chain, the food chain over there will be affected. We really are not in a position to estimate at the 3 kilometers down at least what will be the impact of that value chain loss. Unfortunately, we human beings, we do not have that modeling capacity till date. What is going to be the effect for that? So, IMO and the maritime organizations till have not allowed any of such pumping down of CO2 until this is clear. Theoretically, this is a very good thing, and again, Mother Earth is doing this naturally for millions of years. However, whether it's man-made things as it's good or bad, it is not very clear, so it is still under very much analysis. I think this answers. We do not know the consequence now.
What happens when it is stored?
The moment, first thing with the water, it will form acid. Now the acid of the it is not coral, it is much beyond the coral reefs. There will be some vegetation or some animals living, they will be affected. First thing, The international bodies are not permitting that because do we have the right to affect that or not? Nobody is allowed. Our government is not allowed at least. Anyway, let's come to this. We talked about the EO. Third thing is that coming of the pure capital reservoir. Now, here we identify a storage. Now, typically, we don't have a tank-like surface under the ground, which will be under lock and key. So, we need to find out a typical lock, non-permeable lock, which is on the reverse side. So, you can have a natural structure like this, where you don't have a cap lock, it's called cap lock, which is it will hold that reservoir, and you can push CO2 from side and you can move it, and when they rise, and they actually getting stored in that particular space. And one of the figure yesterday we discussed that over the years, starting from 10 years to 1000 years, there are conversion of the CO2 to the mineral. So that can start as soon as 10 years, 2000 years. Now, this depends on the soil mechanics, soil chemistry over there. We will come to what are those parameters over there, but that's the basic things. Now, I think let's saline microphos, etc. We'll share the presentation so you can go through these. Let us check out what the storage has been done. Now, this is not the enhanced oil recovery sites. Now, you can see on this, the first one with the red one, which is Canada, which is enhanced oil recovery, which is putting already 20 million tons of CO2 has gone inside. Second one, in Salah, which is in Algeria, this is the pure CO2 storage. This is the BP Stratton project where they have found the catalog. They have found the spongy layer between, and they are pumping the CO2 inside, and they are storing this. Till now, it is 17 million ton has gone in, and this is typically earlier a gas field. So they are taking up the gas. Gas is now becoming void. This place is void of gas, obviously not a vacuum, and then they are putting CO2 in that place. So that's the second one. So it can be enhanced gas recovery instead of EOR. And then third, we are talking about Norway. Another 20 million ton has gone in. There it is a saline formation, so there it has gone to aquifer. So let's talk about a few of the things. I'm sorry, I'm moving out. Now, one of the questions came yesterday that, okay, this is that I am putting the gas in, no doubt. Now, what are the options where gas can come out? So, whenever we are designing for BHEL, that next we are trying to do that. What can be our possible geological site? We need to know what can go wrong, first thing. So, if we know what can go wrong, then we know what can be right. So, what can go wrong? Number one, first, there is a capillary pressure through which you can come in. So, we can put out on the left hand side. We talked about, this is first one, CO2 pressure exceeds capillary pressure and passes through. Number two, the fish utilities from the upper surface, if you see the peak. So there is a fault line and there CO2 is going out. First one is the simple capillary action. So these rocks are spongy enough and CO2 naturally goes out. Here it is there, coming in. C is, where is C? Okay. Now C is coming, CO2 escapes through gap in the capillary. So this is the capillary. This is another one, there is a gap inside and where CO2 is finding the fault line and going out. That can be over. D is clearly injected CO2 actually migrates to the reservoir. and go up. So here is the oil well, where they are going now. Or it can be migrate to sidewise. So once after down it migrates either of this side and they can go get the wherever they can get the fault line, they go up. Then CO2 escapes poorly plugged well. So I have a well, I have put it down, I have not plugged it out, and it is going up. Natural flow dissolves, which is there, and dissolves CO2 escape to the atmosphere because the catwalk, it gets into the catwalk and basically this is the catwalk. Huh? This is ground shape is the catwalk and this is where you can store. This is maybe 4-5 meters of layer coming in where you can store, and this is the 20 meter of layer which is the cat, because it will be layer by layer. Now they can migrate over here and in the day some open path they can go out. Maybe 200 kilometers outside after 10 years. So that's the possible things might. So if you know these are the ways where CO2 can escape. So let us talk about how we can plug this out. Now I think I need to give one more thing. I think I don't have a photograph of this because I am not allowed to do that. But this is an example. I think many of you know when the drill goes for digging a hole, and after immediately drill goes, you need to cement it so that there is no caving and breaking of the hole. Now in Algeria, one of the places, again I am not mentioning the name, they went, the hole went in, and this cementing has to be done in single row. Maybe it's a 2 kilometer downhill, but entire cementing needs to be done in a single row. It cannot be. And what happened in that particular site? Well, one of the trucks that had an accident and it actually blocked the cement coming in, and it was a very big concrete. So there was a crack developed between the halfway. And unfortunately, by the way, this is not a EO or CCS site. This is an purely oil exploration site. There was a basically crack in that particular layer, and fortunately or unfortunately, it was a limestone rock was there. And the water seepage has happened, and there was a chemical dissolving happening in that area. And the whole village, with a crater of almost 800 meters, has gone down was almost 20 meters. That the accident has happened. Now, fortunately, because it was happening slowly, there was no loss of life. People were evacuated in that. But this talks about one of the cases what made it go wrong, because my down, even catwalk was fine. But there was a fault while making the well, cementing the well, because in between the catwalk and top layer, somewhere there was a water layer, and the water layer actually seepaged into the limestone layer, and they had an accident, and there was a caving of the entire layer. Now these are the type of accidents happening, and it was horrible to see this. Horrible, like almost a circle. It is not exactly circular, it has gone down, actually gone down. So these things might happen over there. So how we ensure these things? So when we know these things, and these are the things we debated in the United Nations, that what can go wrong and then what needs to be done to make it right. So what needs to be done? Obviously, first one we have to understand. Few of the things is that site selection. Now to do site selections, before you get a license, apply for a license. For a CO site which is CO2, you must have done a site geology, tectonic regime, depth of burial, which depth we are talking about, surface characteristics, likely trapping mechanism, that chemical trapping, mineral trapping, soluble trapping, can you remember that green and yellow we are talking, different trapping mechanisms are there, and anticipated seepage pathways, we have to do, because if your injection site is here, we have to do a radius of at least 50 kilometers where we see where this catalogue is moving, which is my injection capability and where is the possible seepage pathways. We have to model the entire thing out. Now, the site must have ensured that adequate capacity and injectivity. So, if I inject this curve or this upside down, I think it's just like a saucer cup but upside down. That should be having the dead volume. Should be I have mentioned that what is my capacity for that storing that amount of CO2. Now include a satisfactory sealing catalog. That means what is the sealing capacity? How porous it is. Otherwise, we will come down for situations over here. So we cannot come over situations like this. Our ideal situations will be here, but this should be properly done. And the volume should not exceed that one. Then, now I have copied it from the European Union directive. So this is whatever I am putting it. Now it's a part of a law, and we will be handing over European Union directive for site selection, which is approved by Australian board also, and now by United Nations Framework Convention on Climate Change. So if tomorrow you need to do it, you don't need to ponder out what more you can think about. It's very clear what data you need to be collected, very well documented. You just need to go through this. So this is geology, geophysics, geochemistry, geomechanics, seismicity. So what is the earthquake zone? And then after that, you have to do the characteristics of what is the population distribution over here. So definitely, even my bottom size is very good. If there is a population upstairs and we cannot take a risk will come into. So first you need to do this data. Once we get this data, we have to do three-dimensional static geological earth model. So there is no point we get a two-dimensional model. It has to be a 3D model. If you don't get a 3D model, you are not going to get the license. Follow it. So, and once I do the area, vertical extent, pole space and volume, so these are all data you need. After G, once you do the data collection, then you have to do a characterization of storage dynamic behavior. Because in the negotiation team, one thing is that each word makes sense, each word you do not know. So we cannot have the static behavior, we have to do a dynamic behavior. The moment we say the dynamic behavior, the data collection cannot be a single point data. It has to be over the years. How it is behaving, how it was behaving, and we have to predict how it will be behaving. So we have to develop those models coming up. So we have to do it using a reservoir simulator. So multiple simulations might be required and it is required. And again we talked about short-term and long-term simulation. So obviously we need a lot of supercomputers over there. Now what the dynamic modeling gives, what should give. Now this is also in the regulation. So I am talking just copy-pasted from the regulation. So this is nothing my own thing. We have to take the pressure, temperature, nature of CO2 flow in the reservoir, we have to simulate this. CO2 trapping and secondary containment. And so this is the till S. So almost we have finished the entire alphabets. Then you have to come out with seepage monitoring and measurement accounting. So you have to come out with a plan that in case seepage happens, how you are going to monitor the seepage. So you have to give a measurement and monitoring plan of the seepage. We'll monitor well integrity, the atmospheric monitoring, surface improvement, aerial one. And then typically the monitoring, we have mentioned that there are two things you need to monitor through using, which is isotropic characterization. So you have to send out the isotope inside and you have to form where they are traveling. So the moment you put the CO2 in, you need to monitor where the CO2s are moving inside the ground. in a three-dimensional way. So not only you get the behavior previously, before injection, during injection and after injection, even after the closure of the well, you need to monitor the where the CO2 is going. Second is the direct laser absorption sensors. I do not have much idea of what this technology is, but I got the results over there. But this is some electron instrumentation Pandit can take about this, but I am not. But its model looks very fine. And then we have to do a risk assessment. Now this I have copied from a real risk assessment of a real project. So this is there is much more of this. I just thought of this. So we have to talk about the first one, the lab. We have to talk about the lab phase risk, pilot phase risk, and then there is a lot of things. The injection phase risk, what is the implementation phase risk, post-closure risk, and these are not only the risk. Every time you have to risk, you have to categorize what level of risk and what is the management plan of that risk. Now, with all these things, once you satisfy that your probability of success is very, very high. Now, this is the relative point that which country talks about with 90% probability or 95% probability. But typically, it's the probability of risk seepage is more than 2 to 3%. It's very difficult to get the licenses in. Initially, we discussed in the negotiation chambers. I can remember initially Brazil was demanding it's 100%. Then we negotiated. No, it is not possible. It should be 90%. So 10% probability of going out. Finally, still it is not decided. Most probably it is going to be something 92-93% of risk. So then 7 to 8% of probability should be manageable. I think that's what I had on the storage issues. Hopefully we can go in detail, and I very quickly go through another one. Now, can you get this off, please, boss? Excuse me, can you get this off?